Lesson 23, Important Characteristics to Describe. Example 5. The rand_int minimum, maximum random number generator function on the TI-84 calculator is programmed to randomly generate an integer on the interval from a specified minimum value to a specified maximum value. For instance, executing the rand_int 1,6 command on the TI-84 calculator can simulate the random process of rolling a standard six-sided die. The rand_int command is found on the TI-84 calculator by pressing the Math button and arrowing over to the PRB, short for probability menu, and then you could arrow down to the fifth one in the menu is rand_int, or you could just press 5 to get it directly. Then you have to tell the calculator the interval that you want it to randomly generate the integers on. Here we're going to go from 1 and then comma to 6. Close parentheses. And pressing enter, the calculator will randomly generate an integer from 1 to 6. This is as if we had rolled a six-sided die and it came up a 6. Press enter again, we rolled another 6. Press enter again, we rolled a 1. And so every time we press enter and execute the rand_int command, it randomly generates a number as if we had rolled a die. In this case, we rolled a 4, enter, rolled a 3, enter, rolled a 5. So this rand_int command randomly picks numbers from the range that you specify, from the first number, the minimum, comma, to the second number, the maximum number. Use appropriate descriptive statistics methods to describe the important characteristics of the results produced by using the rand_int 1,6 random number generator function on the TI-84 calculator to simulate the random process of rolling a standard six-sided die 100 times. So to describe the important characteristics of data, we need to use words of the problem to describe the three main aspects: the distribution, the central tendency, and the dispersion. The results in this case will be generated by using the TI-84 calculator's random_int 1,6 command 100 times. Now, to simulate the random process of randomly rolling a die 100 times on the TI-84 calculator, we can press Stat, Enter to get to the lists. Here we have some old data from a previous example. I could use my arrow to arrow up to the list name, in this case L2, pressing Clear, Enter, clears out old data of list 2. I could also use my arrows to arrow over and up to the list 1 name, L1, and then pressing Clear, Enter, clears out the old data to make room for new data. So now I could enter in my results into a list, let's say list 1, by pressing the up arrow to highlight the list 1 name. And then we could use the random_int command by pressing Math, arrow over to the PRB, probability menu, and then I could select the fifth one, random_int. And then to randomly simulate the rolling of a die, we can come up any one of 6 points. So we can do 1, the lowest, comma, 6, the highest. But we want to do this 100 times. So we also have the option of pressing another comma and then typing in 100, close parenthesis. And now the calculator will randomly simulate the process of rolling a six-sided die 100 times. Enter. So now list 1 contains the results of that process. Here, first one we rolled was a 1, and then a 3, and then a 6, and a 2, and a 5, and a 6, and a 2, and so on 100 times. To calculate the descriptive statistics for this data, we could press Stat, right arrow to the Calculate menu, press Enter to select the one_var_stats command, and then the list we put the data in was list 1, so second 1, brings up L1. Pressing enter, we see that the mean x bar is 3.47 and the sample standard deviation S sub x is 1.79 and the n equals 100, meaning they did this process 100 times. Now to see if we have any outliers, we need to see if any data values occurred 3 or more standard deviations away from the mean. One way we could check this is take the mean, x bar 3.47, and then subtracting 3 times the number of standard deviations, which is 1.79. Enter gives us the result that is 3 standard deviations below the mean, negative 1.9. And then taking the mean, 3.47, and adding 3 times the standard deviation, 1.79. Enter gives us the range that is 3 standard deviations above the mean, 8.84. And since when we simulated the process of rolling the die, we only get results between 1 and 6, there are clearly no outliers because no data values will occur below the negative 1.9 or above the positive 8.8. So, the appropriate descriptive statistics methods to use when we have quantitative data, which contains no outliers, is to display the distribution of the data. We construct either a distribution table, histogram, or stem and leaf plot. And to describe the central tendency of quantitative data, which contains no outliers, we'd calculate the mean. And to describe the dispersion of quantitative data, which contains no outliers, we'd calculate the standard deviation. These results can all be done on the TI-84 calculator. We've already calculated the mean. The resulting sample mean, x bar, rounds off to 3.5. And the resulting sample standard deviation, S sub x, rounds off to 1.8. Now we could use the TI-84 calculator to construct our histogram. To construct the histogram for this data, we go to stat plots by pressing second, y equals, and then enter to get to plot 1. It is turned on, so it'll be displayed when we press the graph button. The type of graph is set to histogram. And the X list, the data that it's going to base the histogram on, is in list 1. So we don't need to change any settings here. But we do need to set up the window. Xmin is where we're going to start the histogram on the x-axis. Xmax is where we will end the histogram on the x-axis, and XSCL is the scale, that is the amount by which we're counting by. Well, here in rolling the die, we get numbers from 1 through 6. So we're just going to count these one at a time, going from a minimum of 1 to a maximum of 6. So we can go from 1 to 6, counting by 1 at a time. Technically, though, recall that when we draw the bars on the histogram, the bars are drawn in such a way that they completely surround the data value. So technically, if we wanted to totally surround the 1, we really have to go from a range of 0.5 up to 1.5. And if we wanted to totally surround the value of 6, we need to go from 5.5 to 6.5. So technically, we can make the minimum 0.5 so that we totally surround the minimum value of 1. And the maximum value, we can make 6.5 so that we totally surround the maximum value of 6. And the x scale is 1 because we're going to count each one at a time. Y-min is the minimum value. The y-axis on the histogram is the frequency, so the frequency always starts at 0 at a minimum and then counts its way up to the maximum frequency. And since we didn't look at all the data yet, we don't know what the maximum frequency is. So a good guess would just be the sample size n, which was 100 times we simulated the rolling of the dice, divided in half, or 50. After we graph it, we could decide that we need to adjust that, and we could come back and do that afterwards. So here we're going to go from a minimum frequency of 0 to a maximum frequency of 50. And going from 0 to 50, let's count by tens. So the Y scale, YSCL would be 10. Enter. Okay, to see the graph, we just press the graph button. And here's our histogram. Pressing the trace button, we could see that the first outcome, which is rolling a 1, that falls on the interval of 0.5 to 1.5 on the histogram, occurred with a frequency of 19 times. Right arrow, rolling a 2, which is surrounded by the bar on the histogram from 1.5 to 2.5, had a frequency of 16. Rolling a 3 occurred 18 times. Rolling a 4 occurred 13 times. Rolling a 5 occurred 14 times, and rolling a 6 occurred 20 times in this random simulation using the randint command on the TI-84 calculator. So looking at our resulting histogram, we could see that the pattern here, although each bar in the histogram sometimes is slightly higher or lower, the overall pattern is it's pretty flat, equal, or uniform. Thus, we would describe this distribution as a uniform shape distribution. Even though the exact bars are not exactly at the same height, we got to put this in context. This result was due to a random sampling or simulation of rolling the die. And just by chance, sometimes you can get a little more of one value, which leaves you few opportunities to get another value. So in this case, you could see that we happen to have rolled a 1, 3, and a 6 a couple more times than would be expected, leaving 1, 2, 3 fewer 2s, 4s, or 5s. But these fluctuations from bar to bar in the histogram is really due to the result of a random sampling or simulation than due to an actual resulting pattern in the data. So this pattern is best described as being uniform. Now the results that I got here were the results of my doing the random simulation of rolling a 6-sided die 100 times. If you were to duplicate the results that I performed in this example, you would not expect to get the exact same results that I got here. That's because it would be as if you had been rolling your die on your own randomly, compared to me rolling the die randomly on my own. The results wouldn't be exactly the same. But if you really do this on your own, you should check and see that although your random sample results and my random sample results would be completely different, in the end, these overall statistics would be very close to each other. So your mean would be very close to 3.5, and the standard deviation would be reasonably close to 1.8. And the distribution that you would see in your histogram would be uniform, although you wouldn't get probably more 6s and 1s and 3s and less 2s and 4s and 5s. You might get slightly different fluctuations, but overall you would get an equal uniform shape. And that's because the results due to random sampling can vary just by chance. And this resulting differences is just different by a certain margin of error, not that the results are actually anything different. So now we could take these results and use words of the problem to give a good overall description of the data. The results produced by using the randint 1,6 random number generator function on the TI-84 calculator to simulate the random process of rolling a standard 6-sided die 100 times produced an approximate uniform shape distribution with a mean of 3.5 and a standard deviation of 1.8.